Hello, welcome to chapter 3, section 3. Today we talk about the addition rule. So last time we talked about finding probabilities where we're doing multiple actions at a time. So we would multiply stuff all together. Well, today we go back to just doing one thing at a time. So we're just going to do one action, pick one person, pick one card, whatever, but just one thing at a time. So when we just do one thing at a time, we want to use the addition rule in certain situations. Before we can talk about those situations, though, I need to define another vocabulary word. So this is called the mutually exclusive events. So mutually exclusive events are when you have two events that can't happen at the same time. So mutually exclusive cannot occur at the same time. For example, if we have two events, event A being rolling a 3 on a die, event B being rolling a 6 on a die, are the events A and B mutually exclusive? Can you roll a 3 and a 6 at the same time on a die? No. So if you can't do it at the same time, then yes, they are mutually exclusive. And I know it sounds weird because in my brain, I think of it as the opposite, so it's really weird. But if they cannot happen at the same time, no, then yes, they are mutually exclusive. Ugh. So the reason why we want to know this is because when we find probability of things, if you're just doing one action, like rolling the die once, the probability of rolling a 3 and a 6 at the same time would be impossible, right? That's why we said, yes, it's mutually exclusive, because no, they can't happen at the same time. So if they cannot happen at the same time, then the probability of A and B happening at the same time should be 0. So if the probability of A and B has to equal 0 for mutually exclusive events, then that brings me to the addition rule. So the addition rule is us trying to find OR probabilities. If I want to find A or B happening. To find it, we just add the two probabilities together, but we have to make sure that we also subtract out the probability of A and B. So the reason why we do this is when we talk about OR, if we're saying event A or event B, both of those things are things that I want. So remember when we find our probabilities, we do the desired number of outcomes over the total number of outcomes. So what I'm desiring is both A and B. I don't care which one I get as long as I get one of them. So if I don't care which one, then I can just add up the probability for whatever event A is, add it to the probability of B, because then those are the things that I want. But then if there was something that fell between both categories, I would end up double counting it when I add them together. So that's why I also want to subtract that out so that I don't repeat it, basically. So I don't double count the stuff that gets repeated. So that's why we subtract that out. And then like we said before, for that part where it's the probability of A and B, if A and B are mutually exclusive events, then their probability would just be 0. So it's like you're subtracting 0 from it. Okay, we're going to do some examples with our formula so that we can see how this is done. We're bringing back the cards, so I have it over here so you can kind of see. I know it's kind of small. But for the first example, you're going to select a card from a standard deck. Find the probability that the card is a 4 or an ace. Okay, so as we find this probability, I'm going to first just do this visually, without any formulas, whatever. If we go through our deck of cards and we're trying to look for 4s or aces, if you just look through all the cards, we've got aces right here. There's 4 of them. And then 4s are right here. There's also 4 of them. So our probability for this, if we count up all the aces, all the 4s, because these are all the things that we want, then our number of desired things at the top of the fraction would be 8, because there's 8 total cards that I want, divided by the 52, because that's how many there are total. Okay, so if we did the formula, then I also want to think about, all right, I'm just drawing one card. Is it possible to get an ace and a 4 at the same time? No, because these are totally different cards. So when I draw out one card, I'm either going to get a 4 or an ace. There's no way to get both at the same time. So that means because they cannot happen at the same time, these are mutually exclusive events, which means that the probability of getting a 4 and an ace at the same time should be 0. So I can just add up the probability of getting a 4, which is 4 out of 52, because there's 4 4s in the deck of cards. add it to the probability of getting an ace. There's also 4 aces out of the 52 cards. And then we are subtracting 0 because the probability of getting a 4 and an ace at the same time is 0. And when I do that, I get 8 out of 52. Cool, which is what we got from counting as well. All right, for my next example, slightly different this time. You select a card from a standard deck, find the probability that the card is a 4 or a heart. Okay, so now we want to look at cards that are either 4s or hearts. So first, this is a 4, this card is a 4, this one, and this one. Hearts are everything in this row right here. So there's, how many cards is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm counting 16 cards that are either a 4 or a heart. Okay, so technically, if I just counted it out, my probability should be 16 out of 52. Okay, let's try using the formula this time. So the probability of getting a 4 or a heart. Okay, so first, again, I want to make sure, can I get a 4 and a heart at the same time? And the answer is yes, because right here, this card is a 4 of hearts. So this can happen at the same time, which means they are not mutually exclusive events, because they can happen at the same time. The probability of them happening at the same time, so like the probability of 4 and heart, is 1 out of 52, because there is one card out of the 52 that is both at the same time, both a 4 and a heart. Okay, so then if we find the other two probabilities, the probability of the first thing happening, getting a 4, would be 4 out of 52. And then add that to the probability of the second thing happening, or getting a heart. There are 13 cards that are hearts. So when I add that together and subtract it by the one card that's both, I would end up with 17 over 52 minus 1 to get my 16 over 52. And so this is that part where I was like talking about the double counting, because this card, the 4 of hearts, got counted in both the 4 category and the hearts category. So because it got counted twice, we had to subtract it out so that we didn't double count it. That's what I mean by the whole double counting thing. Okay, so one more example with this. This time not about cards. This time you roll a die. Find the probability of rolling a number less than 3 or rolling an odd number. So first, when we talk about numbers less than 3, we mean don't include the 3, because remember, less than means like anything smaller than the 3, but you can't use 3. So that would be numbers like 1 and 2. The other event that I'm looking for is rolling an odd number. So first, rolling a 3 or an odd number, can they happen at the same time? Or sorry, rolling a less than 3 number or odd number, can they happen at the same time? The answer would be yes, because if I rolled a 1, that would be less than 3 and it's also odd. So this is not mutually exclusive. So I would have to take the probability of rolling a number less than 3, which is 2 out of 6, because you can get a 1 or a 2. Add that to the probability of you rolling an odd number, which is 3 out of 6, because odd numbers are 1, 3, and 5. And then subtract out the probability that you get both at the same time, which is 1 out of 6, because there is one way for you to get a number that is both odd and less than 3. Because if you roll the 1, that would be both. So our final answer for getting 3 or less than 3 or an odd number would be 4 out of 6 when I add and subtract those together. Okay, another example using the same formula. So this time we have a frequency distribution. So still finding probabilities, just trying to give you different scenarios when it could happen. So the frequency distribution shows the volume of sales. Remember, frequency distribution is just like us listing out the different numbers, the ranges of numbers, and how many times it occurs. So the frequency is the months. So we're looking at the volume of sales and the number of months a sales representative reached each sales level during the past 3 years. If this sales pattern continues, what is the probability that the sales representative will sell between $75,000 and $124,999 next month? So if they're asking about between 75,000 and 124, we're talking about these two ranges of numbers here. And so because we don't care like which one it is, we just want like the 75,000 to 99,000 or the 100,000 to the 124,000, then we can just add those two probabilities together, knowing that you can't be in both categories at the same time. So if we were to subtract, it would be mutually exclusive when we use the formula, so we would end up subtracting from 0. So we have 7 for the 75,000 to 999,999, and 9 for the 100,000 to 124, 999 number, minus 0. But then because it's a probability, we also need to put it over the total, like how many outcomes are there total. So in order to find that number, we'd have to add all of my frequencies up. When I do that, I end up with a total frequency of 36. So each of my probabilities will be over 36. And I know I should have mentioned this earlier, but I just wanted to make sure when you add fractions together, your denominator doesn't change. I forgot to mention that because I'm like, oh, it's been a long time since you've done fractions, so you should know it, but then I always forget to say it just in case people forgot. Anyways, so when we do this, adding it together and subtracting 0, we end up with 16 over 36 as my probability. Okay, my last couple examples, we're going to look at the different blood types. We're given a two-way table. So again, I'm trying to give you, we're still going to be using the same formula, just different situations, different scenarios of this happening. So this time we're given a table of information and about the different blood types that people have. I don't know that much about blood types, but I know there's like type O, type A, type B, type AB. I know I'm type O. And then then they also have like positive or negative. And I forget what the RH stands for. It's some sort of like genetic thing. I don't know. But I know I'm type O negative. I think that's the universal donor one. Anyways, so for the first example, we are looking for the probability the donor has type O or type A blood. So if you look at the chart, type O are these people here. Type A are these people here. If you have type O, then you can't be in the type A column because you can't have both blood types at the same time. That would be weird. Okay, so because they cannot happen at the same time, then this would be mutually exclusive. We would be subtracting by 0. All right, so since you can't have type O and type A at the same time, the probability of O and A would be 0. So we're going to be subtracting 0. The probability of type O, because we are looking at all the people who have type O blood, we look at this 184 number. And remember, it's supposed to be a fraction when we're talking about probabilities. So 184 out of the total number of people in this study, which was 409. Then we want to add that probability to the probability of you having type A blood, which would be the 164, because that was the total for type A out of the 409. When we add that together, we end up with 348 out of 409. So that would be the probability of choosing someone who is type O or type A. Okay. Then the next situation, we are looking for the probability that the donor has type AB or is Rh positive. Okay, so this time, the people who are type AB would be here. Rh positive are all these people here. And so because we do have this like little cross section here where we have 12 people who are both AB and positive, then this means that it can happen at the same time. That's what we would have to subtract when we use our OR formula. So when I look for the probability of choosing someone who's type AB or positive, we would have to add the probability of someone being AB with the probability of someone being positive, subtract when they're together at the same time. So there were 12 people who are both AB and positive out of the 409 total. All the people who are type AB is the 16 people right here, the total for the ABs. And then the total of the positives was the 344 out of the 409. And then we subtract the 12 over 409 for the people who are both. When I do that, I end up with, oh, that's awkward, 348 again. Okay, that's not always supposed to be the same number, or not always going to be the same number. It just so happened. All right, so this is where you want to pay attention to, can the two events happen at the same time, so that you remember to subtract it out using the formula. All right, that's it for this section. Thanks for watching. Bye.